1.1.7 Example by square roots. 1.1.7 Example square roots by Newton's method. Procedures, as introduced above, are much like ordinary mathematical functions. They specify a value that is determined by one or more parameters, but there is an important difference between mathematical functions and computer procedures. Procedures must be effective. As a case in point, consider the problem of computing square roots. We can define the square root function as the square root of r is, I think that might actually be an x. We'll go with that though. Maybe it's an x. The square root of x is the y such that y is greater than or equal to 0 and y squared equals x. This describes a perfectly legitimate mathematical function, and we could use it to recognize whether one number is the square root of another, or to derive facts about square roots in general. On the other hand, the definition does not describe a procedure. Indeed, it tells us almost nothing about how to actually find the square root of a given number. It will not help matters to rephrase this definition in pseudo-Lisp. Define the square root of x, the y, and such as the greater than 0 and equal to the square of y of x. This only begs the question. The contrast between function and procedure is a reflection of the general distinction between describing the properties of things and describing how to do things, or, as it is sometimes referred to, the distinction between declarative knowledge and imperative knowledge. In mathematics, we are usually concerned with declarative, what is descriptions, whereas in computer science, we are usually concerned with imperative, how-to descriptions. How does one compute square roots? The most common way is to use Newton's method of successive approximations, which says that whenever we have a guess for the value of a square root of a number x, we can perform a simple manipulation to get a better guess, one close to the actual square root, by averaging y with x divided by y. For example, we can compute the square root of 2 as follows. Suppose our initial guess is 1. The quotient is 2 divided by 1, 2. The average is 2 plus 1 divided by 2, or 1.5. Next guess is 1.5. 2 divided by 1.5 is 1.3333. 1.3333 plus 1.5 divided by 2 is 1.4167. 1.4167 is 2 divided by 1.4167, which is 1.4118, which, when you add them together divided by 2, you end up with 1.4142, which is our final answer. Continuing this process, we obtain better and better approximations of the square root. Now let's formalize the process in terms of procedures. We start with the value for the radicand, the number whose square root we are trying to compute, and the value for the guess. If the guess is good enough for our purposes, we are done. If not, we must repeat the process with an improved guess. We write this basic strategy as a procedure. Define. I better put the parentheses. Define square root iteration, so square root iter, guess x, if good enough, guess x, guess square root iter, improve guess x, x, hopefully that's correct. Okay, a guess is improved by averaging it with the quotient of the radicand and the old guess. Define, improve guess of x, average guess, divide x guess, where define average x and y divided plus x, y, 2. Okay. Let's double check these really quick. Actually, let's see if we can get sure. Oh. Okay, good. So we know it works at least. Alright. We also have to say what we mean by good enough. The following will do for illustration, but it is not really a very good test. See exercise 1.7. The idea is to improve the answer until it is close enough so that the square differs from the radicand by less than a predetermined tolerance, here 0.001. So define good enough guess x to be square Okay. Finally, we need a way to get started. For instance, we can always guess that the square root of any number is 1. So, define and x. Okay. If we type these definitions into an interpreter, we can use square root just as we use any procedure. So, oh, I see what I did wrong. I spelled guess wrong. This is why. Okay, so now. Hold on. Alright. So, square root of 9, 3.00000. So now we do square root plus 137. 11.7046, right? And then we do square root of square root 2 and square root 3. And then the square root of 1,000 should give us 1,000. So here is 1,000. Okay. The square root program also illustrates that the simple procedural language we have introduced so far is sufficient for writing any purely numerical program that one could write in, say, C or Pascal. This might seem surprising since we have not included in our language any iterative, looping constructs that direct the computer to do something over and over again. Square root iter, on the other hand, demonstrates how iteration can be accomplished using no special construct other than the ordinary ability to call a procedure. And then, okay.